well my ink behaves, because we all know full well my ink does not like behaving. I gotta find the right slide. Here we go. All right, let me turn the light off. Today's is also the beautiful slide for the timeline. We're trying to keep things, because we have people that are like going remote and they're not remote. So yes, the notes, if you still want to do them by paper, you're not supposed to, but it's what's happening. It's different if you're like quarantined, and then I think like you would attest. And then if it's negative, then you can come back. But did anybody want a paper version? Yes, no. Very canvas. Somebody said that the dates that are on the notes don't want that to be a paper version. No. Curious. The dates are a little off. Miss Castleberry made the drag and drop for the assignment. And then this is actually from my notes, my personal chemistry notes from years and years and years ago. So the dates might be a little off on the year, but they're within the same frame. You need a paper version of it. Good. You need one? All right, so we are taking a look at atomic structure. You guys had some of this Friday. It was simple, okay, and I just don't know the different stuff. I don't know what you did and did not pick, if you guys are reading it by yourself. But that's fine. I'm going to go back over it with my personal notes that I created years and years and years ago. Some of the pictures will be the same. Some of them will be different with what is on that drag and drop, which is the assignment. And like I said, if you did not submit the one from Friday, you need to do it because that's shutting at like 4 o'clock. So some of you may just have forgotten to have submitted it. For this opener, what is matter made up of? What are the bits called? What are all the bits of matter called? What are all matter made up of what? What little things? No, you're going too small. That's too small. Atoms. Okay, they're made of atoms. And then, so that's all matter is made of atoms. Now, different elements, their atoms look different than other elements atoms do. But if you could zoom in on gold, all of the gold atoms, I can speak easily, will look like all the other little gold atoms. Then if next to it I put aluminum, all of aluminum's atoms are going to look like all the other aluminum atoms, but aluminum atoms don't look like gold atoms. And then there are 3 parts, 3 particles of an atom. Well, I heard somebody say it over here. What are the pieces of an atom called? Protons, electrons, and neutrons. Now, we're going all the way back to 400 BC. Is the first guy that we're going to talk about. In fact, there's some stuff on my first slide that you guys don't have on your paper. The very bottom bullet that's on my first slide is the first thing that you guys have to fill in. I am used to teaching chemistry in a certain way, and they do things a little differently here as far as where they put it. So, because I worked for 15 hours the last 2 days, I used my old stuff and then I modified it so that it would fit with what they have for their notes, because all the other teachers use the same note format. Now, you should be able to do today's. I was working on your grades yesterday and the day before. And if I find this class, I haven't put them in parent portal. I have some people that have not turned in a single thing, which is not good, because most of it is locked. There are a few examples. George Brackett, no, he's not, is he? Okay, hold on. Let me do official attendance. You move on to the first slide. All right, so this is notes 11, part 1. Part 2 is tomorrow. If I'm not mistaken. You don't have these first couple bullets. This is how I always used to teach this. Atoms talk to each other. They communicate with each other, not like us. They communicate like a puzzle piece. And like when you put down a puzzle piece, the piece has to fit. Well, the way that atoms fit, the way that they talk, are called their valence electrons. It's the very, very, very exterior part of the electrons. They can't talk with their inside electrons. It's almost like a force field around the outside. And if they have 2 valence electrons, then they have 2 bits that can fit with other atoms. If they have 4 valence electrons, then they have 4 bits that can fit with something else. I get to teach you how they talk. We're not there yet, but this is how they talk. This is literally the language of an atom, is its outside shell. That outside shell is called an energy level. We're going to be normally drawing these using Bohr's planetary model. That's not really accurate, but since we're drawing on paper, or I'm drawing on a board, because it's a flat object, it's 2-dimensional instead of 3, but electrons really move in a 3-dimensional bubble. And then the first shell holds 2, you'll have this, only 2, up to 2, 1 or 2. The second shell can hold up to 8. And every shell after that can hold up to 8, which is called the octet rule. Octet does not mean 8. It means full. The first shell can't hold 8. It's a trick question that we absolutely love to do for guys. What does the octet rule state? It states it wants to be like its noble gas, which yes, normally is 8, except for 4 little helium, which only is 2. Now the first part that you guys have is this bottom bullet, the atom. The atom is the smallest particle of an element that still behaves like the element. If you start splitting apart the nucleus of an atom, do you know what you created? What happens when you split the nucleus of an atom? I don't know. You created an atomic bomb. If you split the original atom, which was called deuterium, and we'll get into that isotope later on, you're literally splitting that proton from its neutron, and you give off massive amounts of energy, and we have nuclear, those big mushroom clouds, and lots and lots and lots of death. Yay! And people die. Yes. But the smallest part of an element that still behaves like the element is called an atom. And each element's atoms are unique. But all of their own atoms are the same as each other. All right, so the first guy, Democritus. We are 400 BC, and we are in Greece. A lot of our philosophical things started here. And not saying that people didn't think about this before, but the Greeks like to write stuff down, so they get lots of the credit. People like Plato, Socrates, Aristotle, Pythagorean. I think it's Pythagoras, but the Pythagorean theorem. But this is a bust. That's the sculpture from like the shoulders up. It's called a bust of Democritus. He actually looks sort of angry in this picture. I don't know. But these guys are the people that wore togas, and they had the little laurel, like the olive branch leaf things around their head. And what Democritus said was, all right, well, all this stuff around us, it's made up of little stuff that we can't see, and I'm going to call them atomas. Atoma is Greek literally for indivisible. That's what it means. You didn't know what the heck they were? This is where we get the word atom from. And then the people that believed him and went along with what he said were called atomists, from the Greek word atoma. I need to do attendance. Okay, so people, since they don't exactly fit, it's this one. It's this one. Okay, so the first one was atom. Okay, so we have Democritus is the first guy. His ideas were around 400 BC. It did coin the term atoma, which means indivisible. He and his belief followers were called atomists. Answer for you, Mr. Hill. I don't know if I'm going to take your stuff or not. I don't know. It doesn't say. I don't know. Nathaniel, which I did not see yet. Tyson. Caveman is not here. Emma. Lily, Grayson, Usher. Minnesota, Trevor. Douglas, Tucker. George is not here. Does anybody know if George is sick? Oh, that's right. You said he moved, but I think he's still on my roll. Okay. Sometimes it takes a while for stuff to catch up. I have no control over that. All right, next individual is almost 2,000 years later, the early 1800s. We had a Quaker by the name of John Dalton. John Dalton? He basically said the same thing as Democritus, but it had a little bit of a spin on it. He said that everything was made of these little things called atoms. He got that term from Democritus's term, atoma. Now, he said that they were indestructible. Now, we know that that's not true, but this was the next part in the process of how an atom looks the way that it looks. So, Democritus's was indivisible, Dalton's was indestructible, and they looked like a solid sphere. There were no protons, there were no neutrons, there were no charges. Just like a little BB. And when I pull up his, it literally looks like a BB. And if you have the opportunity to actually be around a scanning, tunneling electron microscope, you can look at atoms, and that's exactly what they look like. You shoot electrons at electrons, they repel, because like charges repel, and you see that outer boundary that looks just like a solid ball. That is what atoms look like in these microscopes. Let's see. So for his, we have Dalton's model, John Dalton. He was in the early 1800s. All elements are composed of atoms, so the same thing as Democritus. They are the smallest particle of matter. They are indestructible, according to him, which we know is wrong, but that's what he said. Atoms of the same element are identical to each other. Compared to atoms of different elements, they look different than the other element. But the element itself, its atoms all look the same. And that's a photograph of John Dalton. We had photographs this early. People didn't smile in pictures back then because it took you standing still for 20 minutes to take a picture. Remember the last one?
What was the last one again?
Which one? On John Dalton?
Yeah, the atoms.
Atoms of the same element are all the same in relationship to each other. Of different elements are different of atoms of other elements. Within the actual element, they're all the same. They're identical. But if you start comparing atoms of different elements, they're unique. So gold atoms have specific properties. Sulfur atoms have specific properties. All of sulfur looks the same, but sulfur does not look like gold. All of gold looks the same, but it doesn't look like chlorine. But all the chlorines are the same, but they don't look like uranium. And all the uraniums are the same, but they don't. Each element is unique. And your element is actually controlled by the number of protons. Its properties are actually controlled by the valence electrons. I said that's how they talk. I just need to teach you their language. And if you guys go off to biochemistry and organic chemistry, you need to approach it like a foreign language. It is how they talk to each other with electrons and special things we call enzymes. Just trust me, you can't memorize it. Unless you got a photographic memory, kudos to you. Gosh, in this biochemistry, I understood it and it was so hard. All right, Thomson model. Now I have a couple videos that we're going to watch. J.J. Thomson. We're also in the late 1800s, early 1900s. So we're about 100 years later. And we had this wonderful invention called electricity. You only had electricity if you were in the city. If you're out in the country, you still use candles and horsepower and all that stuff. And what he did is he had this big, gigantic thing called a cathode ray tube. And the electricity went out of the cathode, shot across the interior part of what looked like a light bulb, and a sealed glass container that was a vacuum. This beam would shoot across inside this glass, and then it would enter into the anode out the other side, and then it would recycle. The video that I have shows this guy with Thomson's experiment, and what he does is he brings a magnet towards the electrons, and electricity is electrons. And when he puts the negative by the electrons, which are negative, guess what happens to the beam of light? You know what happens when you put two lights together? Do they attract or repel? What do lights do? They do what? No. Positives and positives or negatives and negatives repel from each other. Okay, so when he brings the negative in, the beam literally bends away. And when he flips the magnet over and brings the positive to it, it actually is attracted to it. And then through mathematics, J.J. Thomson figured out that the mass of these things was about 1/2000th the size of the atom itself. And we were dealing with hydrogen. Hydrogen has one proton and one electron. It doesn't have any neutrons in its normal state. And he didn't call them electrons, he called them corpuscles. The term electron came later. But he did figure out that these corpuscles, which were later called electrons, were negatively charged. This is how I abbreviate electron. The E for electron, the minus because it has a negative charge. And we didn't have protons. We didn't have neutrons. We didn't even have a nucleus. We just had these negatively charged things. And knowing that an atom was neutral, that they were suspended in a positive goo. We didn't know what that goo was. Now, he called his model the plum pudding model. This is J.J. Thomson, and this is a representation of his model. It was called the plum pudding model because in England, it's sort of like banana pudding, but it tasted disgusting. So we take plums and suspend them in this like custard, which was like had no flavor whatsoever. But that's similar to banana pudding, just not with the wafers and the bananas, and it wasn't sweet. So the chunks, those are the electrons, and then the custard, the goop, that was something that was positive. No nucleus, no electron rings, no protons, no neutrons, just negatively charged electrons suspended in this positive goop. And then I can show you the video. I need to change how I am presenting so that my online students can see what I am doing. Bear with me, my online students. I'm going to share my screen completely with you. Come on. No, I can't do it that way. In order for you to hear, I have to actually share. I have to share this. Now I'll come back. If you missed something, I'll come back in just a second. Now I have to mute. Hold on. Hold on, look at Jessica. I got to mute myself. Otherwise, you're.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray. And he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and See what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving, it's being repelled, isn't it, by the magnet? When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom in something 2,000?
Let's unmute me. Let's change it to my Chrome tab. Sorry, I got to switch everything around. Atomic theory and structure share. Okay, so this was, like he said, this was the first time. You make sure that I'm not double. I am. This was the first time that we found something that was smaller than an atom. It's 1 over 1,800 times. That's how small they are compared to the atom itself. And honestly, most of the atom is made of the nucleus, so it's that much smaller than a proton. All right, next guy, Rutherford, Ernest Rutherford. And we are in the early 1900s. I put my paper in the early 1900s. I have the date in 1911. I think on the Google slides it has since 1913, I think, but it's the early 1900s. I gotta see. Let's see here. Zapped with electricity, the atoms give off rays. Particles he proved were negative charged. Proves that atoms were composed of particles that were smaller, which is the electron, which he called a corpuscle. This also predicted the existence of positive material in the atom since the overall charge on the atom is neutral. That's how we knew that goop, the pudding part of his model, was positive. Now, Ernest Rutherford, a lot of the people that did discover this stuff were in England at the time. Some of them were German or Danish, just because that's where like the education was going on at the time. Our country was still rather new. We actually brought a lot of physicists over from Germany a little after this time. But like I said, we had this big discovery, not really discovery, but the ability to control electrons to be able to harness electricity. And the two charged particles were discovered first. Because with electrons, they repelled from a negative. Protons were attracted to a negative. And that's how and really, he didn't discover the proton. Ernest Rutherford, with his gold foil experiment, which I have a very short video for this too, he figured out that most of an atom was a positively charged subject. He shot these things at gold foil, and most of them passed through, but some of them bounced back. And in order for a positive to bounce off of something, it has to bounce back off of a positive. Otherwise, it's attracted. And this is a representation of his experiment. Once again, not the proton. Poor Goldstein always gets left off. Goldstein's actually the one that gave the term proton to the proton. Rutherford was the one that discovered that the core of an atom, its nucleus, is positively charged. So this is now our up-to-date atom. We have a positive nucleus, not protons and neutrons. We have a positive core, and then going around it are the negatively charged electrons. And I'll probably come back and do his, look, because this is a 45-second long video at the end, as long as I don't forget. So you need to know that J.J. Thomson's the electron pumping model. Rutherford positive nucleus gold foil experiment. Democritus was the first, gave us the term for the atom. Dalton was the one that said that they were the solid spheres and they were indestructible, which we know that that's not true, but that's the way that they work. J. Thomson was the one that proved that there was something smaller than the atom, which was the electron. He just didn't call it the electron, he called it a corpuscle. James Chadwick, I'm going to go forward in time and then go back in time. James Chadwick was a student of Rutherford. And the problem with the neutron is it's neutral. It was really easy to figure out the electron. It was really easy to figure out the proton. This was sort of like the missing glue. Because everybody knows if you have two positives, they repel. So they couldn't figure out if the entire center was positive, why it didn't just explode. Well, the magic glue is called a neutron. They have things in them called gluons. We're not going to get into quantum physics. It's literally the glue, literally called a gluon, that holds your strong nuclear force, the center of your nucleus, together. Otherwise, it wants to blow up. And if it blows up, we have atomic bombs. Or at least we have radioactive elements. So James Chadwick, in 1932, was the one that figured out the neutron. Now we're going to go back in time. Niels Bohr, who was Danish. So also the early 1900s, Niels Bohr is the one that created what was called the planetary model for electron rings or shells. This is how we still draw electrons around a nucleus on paper. It's two-dimensional. It's not right. But we still draw them using his specific model, where the first shell holds two. This is a picture of Niels Bohr. The first one holds two, maximum. We can hold one. Hydrogen has one, helium has two. Then we're going to start filling the second shell, which can hold up to 8. No more than 8. Then we can fill up the next shell, which can hold up to 8 more. Now this one only has 2, so this is 1s2, 2s2, 2p6, 3s2. This is magnesium, is this element. I will teach you what the heck just came out of my mouth. So you need to learn how to read that thing. In fact, next week, you're going to make your own. You need to not lose it. If you need to, you can take a picture of it and upload it into Canvas, because that's going to be your cheat sheet. So Niels Bohr, let me make sure we didn't lose anything. That's all that's on that one. So planetary model, they go in rings, just like planets do, around their center, like our sun. So the nucleus is essentially the sun. All right, next guy, we got, oh, it's animated the wrong way. This is Erwin Schrödinger. Some of the images I have on him, he looks like something out of Harry Potter. He was different. You have to be different to enjoy quantum physics, which is like a very upper level calculus. He invented the math for this stuff. So we have Erwin Schrödinger. He developed the equation upon which quantum physics, or the quantum mechanical model, is founded upon. That there's bits of the bits. It's smaller than protons and neutrons. They have things called quarks. He's the one that figured this out. The way that electrons move in pairs and they have opposite spins, and that SPDF stuff I was just rattling off from looking at the periodic table. They all came from him. His model does not put electrons in rings. It puts them in three-dimensional bubbles or clouds. Okay, so your S's are spherical. So the nucleus is in the very, very, very center. This is the first S cloud, which holds 2. This is the second S cloud, like the sphere, which holds 2. Each P suborbital holds 2. So you have 1, 2, 3, 4, 5, 6. 6 plus 2 is 8. P's look like 2 balloons that have been tied together in the center, almost like a dumbbell. literally two balloons that are tied together in the middle. Let's see, what else do I have on here? I know there's more. They're no longer in shells. They're in three-dimensional bubbles. The mathematics he used calculated what were called probability waves. Electron locations are based on probability waves. And then electrons are said to be positioned in what outside of the nucleus? In energy levels, specifically three-dimensional clouds, not rings like a planet. Electrons are weird. They can be in more than one place at the same time. It's almost like a teleport. Now, there are some questions you should be able to answer down at the bottom. Who coined the term atom around 400 BC? What did it mean? Niels Bohr said electrons move around the nucleus. How is this theory different from Erwin Schrödinger? Schrödinger's was three-dimensional. Niels Bohr was flat. It was 2D. And then the difference between J.J. Thomson's and Ernest Rutherford's. Remember, Thomson had the positive goop, and then Rutherford put it in the nucleus. There were no protons. Now let's see. You guys, let me freeze this. Actually, I'm going to take this book. I need to double check online, make sure nobody else popped on. I need to stop. And then those of you, I think Autumn, you were here and then you left. I'm going to upload this in just a second. In fact, I'm going to stop recording it.